One of the things at CWNP that we've recently done is we have released the first digital edition official study and reference guide, and that was for CWAP. And we will be releasing the same for all of our certifications over the coming year. And one of the things we're including with the digital edition is a set of simulations that can be used to understand wireless concepts. And so what I want to talk to you about today is how these simulations can be used to learn and understand these concepts. In the process, we'll be learning and understanding these concepts together. And of course, we will make sure that this webinar is recorded and archived on CWNP TV. We'll also include a link to it within the digital edition of the study guide so that students can use it to learn and understand these concepts as well. Now, we're not going to be going through a lot of slides today. I'm actually going to be taking you into the simulations and letting you see how they work and what they're going to be doing to help you master and understand these wireless concepts. The key thing here to understand is that they are simulations, and simulations are not real. That's why it's called a simulation, right? And so it's very important to understand that they are used to help us understand concepts, to help us illustrate concepts, but they do not necessarily perfectly reflect reality. Now, it is also important that I note to you that I am originally from West Virginia in the United States, and that means that to me they are simulations and not simulations. So the proper way to say it, a lot of people don't know this, but the proper way to say it is simulation. And so now you'll know that. All right, so we're going to go ahead and move the slide out of the way and start simulating reality. Okay, so first of all, when you go into the digital edition of the study guide, you will see a section called simulators, and this is where you can access the various simulators to understand what they do and how they work, but they're again here to teach concepts. So the first concept we're going to talk about is one that is challenging often for people beginning to study wireless, whether that's Wi-Fi or some other wireless communication system, and that is the concept of modulation. Now, for some of us, we're a bit older, and we come from a time period when modems were very popular, and we used them to dial up and connect to bulletin board systems, eventually the internet. So those of us that are even older, we remember dialing up to BBSs, and then those that might be moderately older remember dialing up to the internet. But we connected this thing called a modem to our computer, or maybe we had one built into the computer with an internal adapter, and connected our RJ11 telephone line to the modem. And then if you picked up the phone while connected, you would hear all these squelches and screeches. And that's because it was using audio signals to modulate digital data. So it was converting digital data into sound, and the different sounds meant different bits. And that was a form of modulation. So ultimately, modulation is just using any medium to convey information. And therefore, you could technically say that as human beings, we modulate all the time. I'm doing it right now as I'm talking to you, and you're demodulating as I'm talking to you. You're taking the sound waves that are coming out of my vocal cords, going into a microphone, traversing across the internet, and then coming out of your speakers, and you're demodulating those different sounds. And we have an agreed upon communication system known as the English language that we're using right now for this communication. And so when you demodulate and decode it, you're able to understand the concepts that I'm attempting to convey to you. That's effectively modulation as well. But within wireless, what we have to do is we have to have some way to manipulate the electromagnetic wave at a given frequency so that it represents different bit values. So the first thing we do is we establish that we're going to communicate using bits. Thank you, Claude Shannon. And with these bits, at some higher layer, they're eventually going to mean something. But at the modulation level, all the system needs to know is I'm supposed to modulate the following bits. And then when it receives it on the receiving end, it says, I'm receiving these bits. And it doesn't really care what those bits are as far as the payload goes. It's just going to pass those up through the layers of the networking stack. And eventually it's going to get to a point where those bits are meaningful in some way. So at layer 2, some of the bits will represent MAC header information. At layer 3, some of the bits will represent IP layer information. At layer 4, TCP, and on, till eventually we get up to the potential top where combining multiple communications together, all these bits may come together to represent a PDF document or to represent an image or to represent an email message or an MQTT message for communications or whatever it is. The point is that the physical layer doesn't care. It doesn't care what that upper layer stuff is. It's just responsible for manipulating the waveform so that it can represent the bits that it wants to represent. And on demodulation, so it can attempt to understand the waveform and what bits it's intended to represent. That's modulation. So let's see if a simulator can help us understand some of this. Now, first of all, what I'm going to do is show you the 802.11 standard. So here we're looking at the 802.11 2020 version of the PDF document. And you can see on this one particular page that I'm on, page 2823, that there are, it looks like 4 different diagrams. There's a diagram up here labeled BPSK. There's one labeled QPSK. There's one labeled 16 QAM and one labeled 64 QAM. Now I say QAM, you say QAM. Let's call the whole thing off. It stands for Quadrature Amplitude Modulation, right? So that's what we're dealing with here. So here we have binary phase shift keying, BPSK. Here we have quadrature phase shift keying, QPSK. And then we have 16 QAM, which means it's quadrature amplitude modulation with 16 different targets in this case. 1, 2, 3, 4 in each of 4 quadrants. 4 times 4 is 16. And here we have 64 QAM, which means we have 64 targets. And if you look, we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 in one quadrant. We have 4 rows of 4, or 16 in a quadrant. 16 times 4 for all 4 quadrants is 64 QAM. Now, the reality is that if we go up to 256 QAM or 1024 QAM, or what is often called 1K, or 4096 QAM or 4K, then all we're saying is we have that many targets, right? That's the number of targets that we can try to hit in the constellation. Now, the way I'd like you to conceptualize this is to think about it as we have a finite real space, and in that finite real space, we're positioning a certain number of targets. When we have a few targets in that finite real space, it's easier to figure out which target we're trying to hit. When we have more targets in that finite real space, it becomes harder. So imagine it like a box, and in that box, we have just 2 targets. So there's a fair amount of space in our little virtual box that we're thinking about, right? And so if there are only 2 targets, we can probably guess, even if the person trying to hit the target is off by a little bit, we can probably still figure out which of those 2 targets it is pretty easily. And then when it's 4 targets, probably still fairly easy. 16, a little more difficult. 64, it's getting more difficult still. Now imagine you've got 4096 targets in that exact same finite space. We haven't enlarged the physical space. The physical space is the same, but in that same limited confined space, we're now trying to hit 4096 targets. It's going to be much more likely for every attempt that we do not detect the target appropriately. Now, what can we do in order to appropriately hit the target and appropriately detect the target so that we're, in other words, more likely to hit our target? Well, what we can do is make sure that any distractions are out of the way. We want as few distractions as possible when we're trying to detect more targets in a finite space, right? So what does that mean? Get distractions out of the way. Well, in wireless, that means we want as little interference as possible. We want as clean of a signal as we can possibly get, meaning that the difference between our signal and all the other noise in the environment is as big as possible. We call that difference signal to noise ratio, SNR. And this is why the higher your modulation rate, so we get up to 4K modulation, we need a super good SNR. But when we're way down at BPSK modulation, we can have very little SNR and still get our communications through. So this is what we're talking about when we talk about modulation. Now, I'm giving you the concepts. I'm illustrating it to you with examples and analogies. Now what we're going to do is we're going to look at simulating this. So let me move this out of the way. And let's bring up our modulation simulator. So with RF modulation, remember what we're doing is we're sending bits, right? We're just sending bits. And I'm going to zoom in on this a little bit for you. Okay, so let's start with BPSK, binary phase shift keying. And we've got some bits in here that are in here by default. If you do have the digital edition and have access to this, just note you can change these bits to anything you want. So for example, I could change it to 0000100, 001 100, 011 100, 010 100. And then if I click Start Simulation, off it goes. So we've got 3 zeros, it looks like, to start with. And so you'll see our first 3 symbols that go by are unchanged. But then the symbol changes. A 180-degree phase shift for the 4th bit, and then we do a shift back again for the 5th bit and the 6th bit, and for several bits. So you see the waveform on the left, and on the right, you see the constellation, the target that we're aiming for. What are we trying to hit? Now, obviously, in real time, with our wireless communications, these radio frequency waves or electromagnetic waves travel in free space at the speed of light. They travel very fast, right? So we're not seeing it as slowly as it's represented here. It's represented slowly here to give us the time to look at it, to understand it, to see what's going on. The point I'm wanting you to get through this simulation is that we have a particular waveform that we're generating every time we want to hit a particular target on the constellation. And then when we want a different waveform, we're after a different target. Now, because this is BPSK, we only have 2 waveforms, and we'll use a waveform during a symbol period, and then a waveform during a symbol period, and then a waveform during a symbol period, and we'll change the waveform in a symbol period if the bit's going to change, as long as the bit's going to be the same. So if it's all zeros in a row, we can keep using the same waveform, one symbol period after another. But if we're going from 0 to 1 to 0 to 1 to 0 to 1, then it will have to change in every symbol period. So for example, if I come up here and I make this 101010101010101010101010, I have to do at least 16 for this simulation. But the point is, if I just keep switching back and forth, you're going to see that for every symbol period, it's going to change to a different waveform. And that's because I'm going from 1 bit to a 0 bit to a 1 bit to a 0 bit. And so it continually adjusts the waveform for every symbol period. But if instead we just have all zeros here, then you can see that for the whole simulation, nothing's ever going to change. Because in every symbol period, and notice those vertical hyphenated gray lines indicating a symbol period, right? a period in which we will look at the symbol to see what it represents, hence symbol period. And so what we're doing is looking through these concepts and understanding how the waveform works. Yes, the simulation are available with the CWAP-405 Digital Edition and with the CWAP-405 e-learning. And again, they will be available with the digital edition of CWNA next. That will be coming out in the next 45 days. Okay, so now that's BPSK. What if we go up to quadrature phase shift keying? And then let's take a look, for example, at 00, 01, 11, 10. So all 4 possible combinations, and then we'll just duplicate that a few times. Now when we start the simulation, you'll notice that we have 4 quadrants and 4 targets. So instead of just 2 targets, we have 4 targets. For every symbol period, because I have manipulated it on purpose, for every symbol period, the target is changing in this case because I've intentionally created the bit series that would do that. And so we can see that when we're modulating 00, it's the lower left target. 01, it's the upper right target. 11, I'm sorry, upper left. 11 is upper right, and 10 is lower right. Now, here's the interesting thing. If we take a look at our specification, notice with QPSK, 00 is the lower left, 01 is the upper left, 11 is the upper right, and 10 is the lower right. So as we run our modulation simulation again, we're seeing that it's simulating that bit representation pattern. Now what you're beginning to see is that with BPSK, yeah, we've got 1 bit per symbol. So it's a 1 or a 0, or a 1 or a 0. But now it's a 00 or a 01 or a 11 or a 10. So the same time period, the same symbol period, can represent 2 bits at a time instead of representing 1 bit at a time. And that is because we're using more waveforms. We have 4 different phases. Instead of only having 180-degree shifts, we have 90-degree shifts. And therefore, we have 4 different phases, and we can therefore represent 4 different chunks of data. And those 4 different chunks of data, because we're dealing with binary, happen to be 00, 01, 11, and 10. Now, the next level that we can go to in this simulator, and we only go up to 64 QAM because, let's just be honest, it serves its purpose at that point, and going up to 256 or 1024 or whatever would kind of be overkill for the purpose. So for 16 quadrature amplitude modulation, now what we're looking at is this constellation diagram right here. Now you can see that each target represents 4 bits, and it contains every possible combination of zeros and ones from 0000 to 1111. Okay, so here we see 0000 in the lower left, and in the far lower left, and in the lower left of the upper right quadrant is 1111. So these are the actual mappings for what the different waveforms represent. And by the way, there's a mathematical reason behind these mappings. We're not going to get into that level of detail because you don't need to know it to be an excellent wireless engineer, unless you're actually building the radios. And if you're building the radios, you have to know the math behind why this does what it does. But basically, we can see then that we've got 4 bits per symbol. 4 bits per symbol. And so we're going to modulate the same waveform for the symbol period, and then keep it the same if in the next symbol period we want the same 4 bits, but change it if we want a different 4 bits. Now, no matter what string of bits, you might have 1,000 ones and zeros in a row. No matter what string of bits, some combination of all of these different 4-bit values can be used to represent that 1,000-bit string of ones and zeros. Okay, so if we take a look at 16 quadrature amplitude modulation now, and let's just, for our constellation that will be over here, let's just do the lower left quadrant, which is 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0. And then we start the simulation. And you can see we've got the far lower left. We should go up next. Then we'll go over. Then we'll go down. Okay. And now you can see that in the modulation, we're not just dealing with phase shifts. In fact, look close. We didn't shift the phase. We shifted the amplitude. Wonder why that would be? Well, it's because we stayed down in that phase. And so we're dealing with amplitude shifts for this communication for the most part. Now, the amazing thing is then just shifting 2 parameters, phase and amplitude, we can get up to this point now where we have 16 possible targets. And of course, if we go to 64 QAM, and I'll just plug in some values here, any kind of random values, just so we can see it. And we fire off the simulation, you can see that we have many more targets now in all of our various quadrants. And we're going to be seeing phase shifts and amplitude shifts and all of that in order to get this done. Now, understanding this, that this is modulation, is an enlightening benefit, because what it does is it helps you fully realize why you need improved signal quality to get higher data rates. So do you notice now we're pushing 6 bits per symbol through? Every time we have one of these symbol periods, it represents 6 bits instead of 4 or instead of 2. And so the reality is, or instead of 1 bit, the reality is that we can go even higher, right? 256 QAM, 1024, 4096, and so on. There are several things that you can benefit from this. One is if you're going to design a wireless network, understanding that what you're really trying to do is improve the ability of your devices to demodulate signals at higher data rates. Then you know, of course, your target is SNR, signal noise ratio. But if you just go around and you say, oh, I need 25 dB of SNR, you've always got this lurking question of why. Why do I need 25 dB of SNR? Why isn't 20 good enough? Why isn't 15 good enough? The more you understand about modulation, the more you begin to understand the benefit of this and how it plays into your ability to get those higher data rates. And it helps you understand why a device does dynamic rate shifting down to lower data rates as the signal quality degrades, because it can't get the transmission through. It's trying to hit targets, but it's failing. Let's see if we have a simulation to help us understand that. So here we have the RF noise simulator. Now, this was born out of a research paper that I read, published by MDPI. And it was talking about IoT protocols and the fact that with IoT protocols, the highest data rate is not always what you're after, but sometimes you're just after getting data through, even if it's a low data rate. And they showed these really great graphical representations of the received signal and what it looked like in comparison to the ideal target. All right. So what I've done is I've built here this simulator that allows you to look at, well, let's start with BPSK, binary phase shift keying. And if we start with a great SNR of 30, which a Wi-Fi device, by the way, would not use BPSK if it's performing appropriately with a 30 dB SNR, it would change to a higher modulation rate, right? Because it can push more data through. But if we click start, you can see everything is right in these target areas, really nice. And so you can see how that as it would switch back and forth, we're not getting much of a buildup here because we've got such good SNR, right? So the receiver is seeing that nice and clear. However, if we change this down to just 5 dB of SNR, let's take a look at the difference. Now do you see that even when our target is on the right, some of it is going to the left. When our target's on the left, some of it's going to the right. But statistically, we would still be able to figure out probably 98, 99% of the symbols. We'd be able to get it statistically right. Excuse me. And so with BPSK, we could have really even down in the 0 dB of SNR, and we'd still be able to get around 90, 89% of those received signals right. Because remember, we've got a finite space we're looking in, and because we're only representing one of two things, they can be as far apart as possible in that finite space, making it more likely that we're going to be able to demodulate appropriately with low SNR. Now let's just jump right up to the biggest. We'll go up to 16 quadrature amplitude modulation. Now that's the biggest that this simulator supports, to be clear. And let's look at it with 30 and click on start. And you can see, you know, kind of for each symbol we're sending through, that it's a little off target. So over time, we're getting this kind of blob representation, right? But if we stop that and let's go down to 20, now we're getting a bigger blob over time, aren't we? As all of our symbols are trying to hit that target, and then at the receiver. So at the transmitter, it might be going out nice and clear, right? But by the time it gets to the receiver with the noise in the environment and so forth, what we're perceiving can be very different. And transmitters don't necessarily perfectly send out the target in the first place. There is a reason why some devices have higher quality than others. There's a reason why an enterprise-grade access point is a better device than a consumer-grade device, if it's a true enterprise-grade access point. So now let's take this down to just 5 dB of SNR. Now look at that. We're all over that lower left quadrant when even we're trying to hit just the one particular target. So it's getting much more challenging. And if we go down to 0, well, you get the picture. We're all over the place. So all this is intended to do is help you visualize that as the signal to noise ratio degrades, the receiver's view of the signal as opposed to the noise of the environment also degrades. And we're able to get less and less of the data. Now, the reality is that even at just 5 dB of SNR, you could demodulate well over 50% of the received signals with 5 dB of SNR. But when you get up to 64 QAM and then certainly 256 and higher, then your ability to demodulate because of the poor quality of the overall signal, that is the signal compared to the noise, ends up getting to where that you're down at only 5% accuracy or less or something like that. And so the higher the modulation, remember, the more those targets in that constellation diagram, the more targets in a finite space, the higher the modulation, and therefore the better signal quality that I need in order to effectively demodulate them. And that is what this is illustrating. Now, another area of common confusion, co-channel interference, CCI. So the point of this simulator is to drive home that CCI is not caused by access points. CCI is caused by wireless stations in the same channel. And those stations may be access points, and they may be client devices. So the reality is that the CCI is caused by any and all wireless stations communicating in the same channel. So we'll assume, we're looking at channel 1, right? So right now, my footprint for this channel is not just that which is generated by the AP, which is right around in here, right? But the footprint for this particular single channel actually extends out here because of this client. It extends out here because of this client, and it extends out here because of this client. And in fact, I could add more clients, and you can see that in my little box, I'm now covering much more of the space, even though the AP itself is still covering the same space that it was covering, but my client signals are radiating out in other areas as well. Now, right now, because there's only one BSS, there is no CCI. Okay? CCI is going to occur with co-channel interference. Other devices on the same channel from other BBSs. Boy, I am old and you can tell it. Other BSSs. So if I add, let's say 3 APs, and we'll give AP3 8 clients and AP2 6 clients and AP1, I don't know, maybe 4. And we'll click simulate. Now notice what we have in this space is we have clients clustered around the AP they're associated with. But look, for example, here you can see that this client, its signal is going well into this area of the red AP up here. And this client is going well into the signal area of the red AP. And so we can see that in this case, there are plenty of areas where you can see 2 BSSs in the same channel at the same time. Now, if I had even more clients, which is more real world, and I run the simulation, then you're going to see areas where like this client is right here and there are 2 BSSs there. So we're going to have more CCI. And if I add more APs, well, you get the picture. So here we've got this client, 4 BSSs can be seen from the location of this client. But look particularly at this one all the way out here. 2 BSSs can be seen. 2 BSSs can be seen. And it's not because of this AP. This AP signal is only getting out to about right here. But this device is making it so that this client can see that other BSS. And when you come over here, this client can see 3, this client can see 4, this client can see 3. Now we're beginning to see the co-channel interference that's coming into play in more detail. This is one of the reasons why it's so difficult to completely eradicate CCI in 2.4 gigahertz, right? Because you only have 3 channels you can play with. Now, in this case, our simulator is putting everything on one channel because the whole point is to illustrate that CCI is caused by any and all stations that are communicating in the channel. And by the way, this can be a good visualization if you need to explain to a manager, why they're having a problem. And maybe you're coming in as an outside consultant and they don't really have any Wi-Fi experts on staff and they don't understand why putting everything on channel 1 is a big deal. Well, you can, of course, use something like this to show them that. All right, just a couple more examples here. One of the common misconceptions that people have when it comes to wireless signals is that you've got a 20 megahertz wide channel, right? Let's just keep it at that for simplicity. You've got a 20 megahertz wide channel. And so as long as the center channels are 10 megahertz apart, then we should have no interference, right? And in fact, in 5 gigahertz, we say we have non-overlapping 20 megahertz channels. So when you go from one channel to the very next channel, they're non-overlapping. Well, they are non-overlapping in their primary channel bandwidth. But are they truly non-overlapping? Let's see. So I'm going to put my APs really close to kind of represent what you might call co-located APs. So they're 1 meter apart. I'm going to put one on channel 1, and I'm going to put another one on channel 1. So I've got 2 APs, both on channel. I didn't mean to do that. Let me remove that. I'm going to put the other AP on channel 11. Okay. So I've got an AP on channel 1, 1 meter away from my simulated spectrum analyzer. And I've got 1 AP on channel 11. So that's about as separated as you can get, right? In 2.4 gigahertz. Not quite. I could have one on channel 13 or 14, but we're going to deal with worldwide regulatory channel usage, right? So I've got one on channel 1, one on channel 11. My spec an is 1 meter away from their antennas. Let's enable max hold. So we'll keep the maximum signal strength we've seen on the screen. And let's run our simulated spec in. What do you see? You see that, oh yeah, there is a 20 megahertz channel, but we have these little things called sidebands, don't we? And what you look at is, look at the noise floor increased here in the middle. So my 20 megahertz is just from here to here and from here to here. But if you look in the 802.11 standard, at the spectral mask for the various different channels, you'll see that it does have these masks in the standard. And what you have is, yes, you have the channel, and then you have these signal strength fall off boundaries at the side. And basically, what these are is the area where it has to fall off by a certain amount of signal strength in order to meet the spec. And then ultimately, you know, the FCC and other regulatory agencies can test a transmitting device to make sure they're in compliance with that spec and that they're not exceeding what they should with their spectrum utilization. And this is what the spectral mask does for you. So if we take a look at the standard, here we're seeing, now that happens to be for 5 megahertz. Let's move forward a bit here. Okay, so here's a 20 megahertz spectrum mask. Whoops. And what you see is that by the time we get down to 11 megahertz below the center frequency, we have to have fallen off by 20 dB. By the time we get down to 20 megahertz, we have to have fallen off by 28 dB. And by the time we get down to 30 megahertz, we have to have fallen off by 45 dB. Now that's dBr, that's dB relative to the peak power. Peak power is whatever this is. So whatever this is, we have to be 45 dB weaker when we get 30 megahertz below or 30 megahertz above, which means that the signal is still there when we're outside of the channel that we intend to be using by an additional 20 megahertz, both above and below. Think about that, especially for 2.4 gigahertz, right? This is the reality. Now you might say, oh yeah, Tom, but we're 45 dB below the signal by the time we get there. Yeah, and what is the normal signal strength for a signal that you receive? The normal signal strength for a signal that you receive is somewhere at neg 50 something or weaker. So maybe neg 51 or 52 or neg 63 or neg 70 or neg 80. And so okay, neg 45 dB still matters, right? And particularly when you're closer to the device, that's when you're going to see more of the noise floor raised by these sidebands. And the question came in, does this also happen in 5 gigahertz? Absolutely. It also happens in 5 gigahertz. So what does that mean? Well, this has two implications for us. There are two things that we need to understand about this. One is you're raising the noise floor when you add more APs. Okay, so the more APs you add, the more you raise the noise floor. You minimize the raising of the noise floor by lowering the transmit power of the AP, because remember, this is dBr. So at minus 30, at positive 30, above the center frequency, what you're saying is we have to be 45 dB weaker than the peak power. So if I lower my transmit power from my peak power, I'm also lowering those sidebands, right? So everything's getting lowered, okay? So one thing you do when you have high density, you lower the transmit power of the APs to reduce that. But keep in mind, you can only accomplish so much from that, because you're not going to go around and lower the transmit power on everybody's mobile phone and on everybody's laptop that's participating in the cells. So the noise floor is going to be raised by those devices, right? That's reality for any kind of environment. But the point is, that's one thing you can keep in mind. But here, for the future of Wi-Fi, to me, this is the bigger area. Okay, the bigger area is co-located APs. Co-located means that you've got more than one AP in a single box, right? So we've already got these. We call them multi-band APs. First we had dual band, then we had tri-band. Now we just call them multi-band. So, you know, maybe you've got a 2.4, a 5, and a 6 gigahertz radio all in your AP. The reality is that sometimes what you do is you have software configurable radios. And so you may be able to have one that is either 2.4 or 5, and then another one that is only a 5 gigahertz radio, right? That's something that's been implemented before. So if you decide to put both of them on 5 gigahertz, what you don't want to do is have them on two different channels that are right side by side in the 5 gigahertz band. So you may want to use one of the lower channels and one of the upper channels, right? Give significant separation between them, because those two radios, their antennas are now right there in that box together. And so if one of them's transmitting while the other one's trying to receive, the side bands from the transmitting radio are going to massively raise the noise floor of that radio that's trying to receive. And it's going to impact the performance and the ability to demodulate and then decode the data appropriately. So that's, for today and the future, that's really where this comes into play a lot, because we're going to see more and more multi-radio APs as we go forward. I wouldn't be surprised if within 10 years, we're starting to see significant deployments where we have a single AP that actually has 4 or 5 different radios in it, because we're going to see radios for non-Wi-Fi protocols included in the box. We're going to see radios to do 2.4, maybe 2 on 5 gigahertz, 2 on 6 gigahertz, etc. So then making sure that you configure them appropriately is going to be important. Now, vendors should give us help here. They should warn you. If you try to configure a second radio in the same AP on a channel that's too close to the other one you've already configured, it should warn you and say, oh, you shouldn't be doing this. But we can't always rely on the vendors to do that. So we need to understand these issues as well. And so now a question came in, well, why don't we just cut it off? Why don't we just cut it off? I feel your pain, okay? And I understand why you're saying, why don't we just cut it off and not have these sidebands exist? But the thing to keep in mind is, man, if you could go back and have Guglielmo Marconi, James Clerk Maxwell, if you could sit them down in a room and show them what we're doing with wireless communications today, oh, their minds would be blown. they would say, no way. This is what we've accomplished based on my initial mathematical formulas or my initial testing. They would be astounded that we're accomplishing what we're accomplishing. But yet, with all we can accomplish, there's only so much we can do in engineering these radios and filtering. So we do indeed do filtering to try to minimize this at both the transmitter, and we have filters on the receiver as well. So we have bandpass filters, you know, and we try to do things to limit this as much as we can, but we're limited by our abilities to engineer what we can engineer. So it's pretty impressive that we're doing what we are doing. Keep that in mind. All right, so just real quick, I want to show you a couple more things here. So we do also have a simulator of a spec am, just so that you can see, for example, if I have a Wi-Fi AP that's maybe 20 meters away from me, 20 megahertz channel, and then I'm running some Bluetooth. Maybe I've got 6 Bluetooth devices that are, I don't know, 5 meters away. Let's put them real close. And I could do Zigbee. I could throw in a microwave oven here, for example. And we'll go ahead and turn on the max hold and start it. And you can see then what that would look like in a spec am. So this is really just for you to get some experience being able to visualize what a spectrum analyzer looks like and how they might work. And if you don't have the budget to get your hands on a real spectrum analyzer. This is obviously not what's really going on in the real world with real spec ams, but it gives you a really good idea. It's a nice simulation to be able to comprehend and understand that. Okay, so that's another simulator that's here as an example. And then I'll show you one last one, the Fresnel zone simulator. So this simulates the, it simulates and communicates the mathematics to you for Fresnel zone simulation. So the Fresnel zone is either measured as the diameter or the radius, depending on which one you want to calculate. Radius is usually most important because you're really going all the way around the line of sight. But you set the distance and then the frequency, and those impact the Fresnel zone. But basically at the center between the two endpoints, you're going to have the widest area of the Fresnel zone. And we want that to be fairly clear for bridge links and things like that. So we need 60% clearance. We want 80%. That's kind of our target to allow for foliage growth and change like that we talk about with our CWNA studies. And so if we fire this off at 5.8, you can see that it's got a 3.59 meter radius for a 1,000 meter length. But if this was 2.4 instead, then it's going to be wider. It's now 5.59. If this is 900 megahertz, then it's going to be 9.13. So obviously, the lower the frequency, the wider the Fresnel zone, and so forth. So it gives you all the math that's behind it in case you care, and so on. One of the things that we're working on right now, I'll mention as we begin to close this out, is we are working on calculators. So we will also be adding calculators in for the study process. So, you know, you can calculate your link budgets, your free space path loss, earth bulge calculations, you know, all that stuff that you need to do. So we'll be adding those in. We'll be adding more simulators too as time goes by, and help you to understand how these work. And we'll be modifying these simulators based on feedback that we get and so on in order to continue the improvement of it. Again, these are currently available with the CWAP-405 Digital Edition only. They're not available with the print edition. I've had people ask me, hey, can I buy the print edition and then get these? No, we really are trying to help the planet and get people to go digital as much as possible. So they come with the digital edition, and we've added them as a perk to the digital edition to motivate people to get that. They do also come with the e-learning, and they will come with the digital edition for CWNA, CWSP eventually, CWDP, the wireless IoT track, you know, all of the digital edition books as they come out. The simulators will be there. Now, there may be some simulators over time that are only available with specific books. So in other words, there may be some simulators that are really only applicable to CWAP studies. And if that was the case, then we would limit those to CWAP. Right now, these basic simulators that you're seeing are going to be available in all of the different digital edition products. So we'll get that. And we can always, as Anders says, we can always add a bit more to these simulations as we get ideas from the community, and we'll be glad to do that. And so, yes, Anders, when you go digital, you get a bit more.